everyone. After the midterm, we found both of the concepts on midterm of cosets and isomorphism significant and fundamental to group theory, as well as many following concepts like homomorphism. Hence, we decided to gather together and discuss to strengthen our understanding of these two concepts, as well as doing some questions together. Now, each of us will report part of this.
So first of all, I want to introduce the Cayley diagram and Cayley table of derived products. So at the top of the slide, and on the left, here is a Cayley diagram for the cyclic group of D2. And for each knot in D2, it contains a copy of D4. So here it is, on the right, it is the direct product group D4 by D2. And if we want to draw the Cayley table of C4 by D2, so on the bottom of the slide, you can see on the left here are the Cayley table of C4 and D2 respectively. And if you consider each cell, like each once more table in D2, and you inflate each cell to contain a copy of the multiplication table of D2, which is on the middle diagram, and you can get and drawing the little tables and elements names to form the table for Z4 by D2 on the right. Okay, 下一页. And for the cosets of the midterm, here are some common misconceptions that we encounter. So if you consider the group G as a big circle, the subgroup H is, you can consider it as a small cycle inside the big cycle of G, while A is a set inside G, but not a subgroup. So you can consider it as a dot instead of a small circle. And also, if we write the left coset of many tries of A for AH, some of them may give the same coset. So the duplicates should be identified and then removed. Here is a coset problem that I want to share with you guys. So if let A4 be the group of G and let the subgroup be the order of 4, we want to find all left cosets and right cosets. So firstly, recall that A4 is a group with 12 elements inside. So the order of group A4 is 12 and the order of the subgroup is 4. So the index of H in G is then 12 divided by 4, and there will be 3 left cosets and 3 right cosets of H. So if we choose the set A to be 1, 2, 3 and 1, 3, 2, there will be the left cosets as listed. So attach the set A 1, 2, 3 with each element in the subgroup of H. We can get a 3 left cosets then, including H itself. And same for the right cosets. Notice that we can choose a different set of A. So for example, 1, 2, 4 and 1, 4, 2 to generate the left cosets and right cosets. But their outcome sometimes will be the same as the above example. And notice that for this case, the left cosets and right cosets are identical. They are the same. So H is actually normal in G.
Could you please explain more about the sentence like we can choose other sets of a 2 for example 1, 2, 4 and 1, 4, 2 is a general coset, but their outcomes would be the same as above?
Sure. So next I will share screen to describe this example. So if I want to take the example of 1, 4, 2, so firstly, let me write the left cosets of 1, 2, 3 again. So the left cosets of 1, 2, 3, and H is this. So when A equals the set of 1, 4, 2, the left coset of AH is then 1, 4, 2 attached to each element in the coset or in the subgroup of H. So it's so if you search for KD table of A4 online, you can get that 142 is still 142 in this case. And in 142 with the set 1, 2, and 3, 4 is then 1, 2, 4. And for 142 and the 1, 3, 2, 4 is and is. So you can actually see that the two left cosets are the same. So so in this case, they are the same left cosets.
Yes, this makes sense. And if the group is abelian, its left coset is equal to the right coset. Just like in our test for the first problem in the Wednesday, we should only write the right coset since the group is abelian. Hi, I'm Xiaolu, and now I'm going to talk about isomorphism. So what is isomorphism? The formal definition in the textbook is that an isomorphism phi from a group G to a group G bar is a one-to-one mapping or function from G onto G bar that preserves the group operation. That is psi AB equals to psi times psi B for all AB in G. This formal definition seems hard. To think it more intuitively, we worked out our own definition of isomorphism. I personally really love the example given in the textbook in the motivation part. Two isomorphic groups are just like we count numbers in different languages. For example, although 1, 2, 3, 4 in English and Mandarin have totally different pronunciations, they mean the same thing. Similarly, for isomorphic group, they are basically the same thing. We can think that as two groups with same order, same structure of Kelly diagram and Kelly table, they're bijective, but isomorphism is the action to rename all the elements.
Hi, I'm Tianshu, and next we are going to talk about how to prove that two groups are isomorphic or not. Here are some key steps that we need to follow and need to check during the proof of our steps. So the first step is finding the appropriate mapping. We need to define a candidate for the isomorphism, and we can denote it as psi, and choosing an independent variable to fill out the connection between the groups. Step 2, we need to find a one-to-one relationship between the two groups. So this will be demonstrated later. And we need also to find the relationship of onto between the two groups. So these two steps can be combined into one step as finding the bijectivity of two groups. And in the last step, we need to find the mapping we found is an operation preserving action. So typically it's psi AB equals psi A times psi B.
Now we're going to demonstrate some problems. First problem is that show that the multiplicative group G consisting of three cube roots of unity 1 W square is isomorphic to the group G R to the residual classes under addition. So for the group G, we can write a Killy table like this. We can see one is actually the identity, so that it should be 1 W square equal 1 W. Also, we know the group module 3 under addition is just the group of these three. So the Killy table is like the operation is module 3 under addition, and the three elements is 0, 1, and 2. Here, since it's addition, so that the identity is there 0. So 2 times 1 is 0, and 1. Now we can see that the structure of the Clay diagram is similar. By closely looking at this, we can see the mapping is, for example, 1 is to 0. W is to 1. W square maps to 2. From the colors, we can see that it is a 1-to-1 and onto mapping, which is bijective. So the isomorphism is that phi1 equals 0. Phi w equals 1. Phi w squared equals to 2.
It is the isomorphism.
So next, we are going to talk about how to prove D3 is isomorphic to S3. So here we want to show and find an isomorphism between these two groups. So first, we should state the elements of two groups respectively. So for D3, by convention, it is a set of elements which contains E, R, R squared, F, FR, and RF. And for S3, it is a little bit more complicated. First, we should do some analysis and about how these elements can be arranged into cycle notations. So S3 as a permutation of three elements, we have some possibilities. The first one is a cycle containing three elements. The second is one is two elements and one is one. So note that in this case, the one cycle can be eliminated because actually this is typically the identity permutation, which we can ignore this. So in the last case, we have three cycles. Each one contains only one element. So these three can consider as the identity permutation, which is the E element, the identity element of the S3 group. So we need to determine for each possibility what are some possible arrangement of the elements. So for the first one, we have 1, 2, 3, or 1, 3, 2. These are two possibilities. And for the second choice, we can have 1, 2, 1, 3, and 2, 3. And for the last one is just the identity. So here we can see that the order of S3 and D3 are both 6. So this gives us a good foundation to find isomorphism because we need to find the common structure between the two groups. So to validate this, we need to draw the Cayley diagram to confirm the structure and the number of elements. So for S3, the Cayley diagram looks like this. We populate the columns and the columns and rows with the elements and trying to find the product of them. So the Cayley table can be finished. So it's just E, 1, 2. Then 1, 3. Then 2, 3. Then 1, 2, 3, and the 1, 3, 2. So we can leave this just aside and trying to find the Cayley diagram, Cayley table for D3. So it's E, then R, then R squared, then F, then FR, lastly RF. So here we can see that the structure of the two Kelly tables are exactly the same. We have 6 rows, 6 columns, 36 elements possible. So it's easy to find an isomorphism that is mapped between the left and the two. So we can use the theorems that we stated before to confirm this is an isomorphism. So the first one is we need to define a valid mapping. In this case, because the S3 and D3 are having different notations, so we can just claim that we have psi such that from D3 to S3 is a valid mapping, such that for any element in the left side, we have psi x, for any element in the left side x, we have psi x on the right side of the table. The next step is to prove the one-to-one relationship. So assume psi A equals psi B, where psi A and psi B are both in S3, which is the right side of the table. So we can find a relationship that A equals to B in the left hand side. So this is very obvious because the mapping is the mapping is just from the left cell to the right cell. So if two cells are actually the same thing, we can just find the exactly same elements in the left side. The next one is to prove the onto. So assume we have for any y is in S3, which is the right side, there exists an x element in D3, which is left side of the table. So this is obvious as well, because if we find any cell on the right side and with the mapping, we can find just exactly this element in the left hand side of the table. So this mapping is also onto in this case. So such that psi x equals to y. The last step is to prove the psi we define is operation preserving. So for any psi a b equals psi a times psi b, so operation preserving psi a b equals psi a and psi b. We can also see this from the Kelly table. Say we have, let me clean this one first. Say we choose 1, 3, and 2, 3 as A and B. So we want to find psi A and psi B, which is R squared and F. So psi AB, which is this cell, and if we check the left-hand side of the table, so AB is this one, and we know that the mapping we just defined is bijective. So psi AB just can have a relationship with this right-hand side size table cell. So this also validates the operation preserving quality. So overall, this is a valid isomorphism, which means D3 is isomorphic to S3. This is the end of our video. Hope this video will help your understanding about cosets and isomorphism.